Hello everybody and welcome back to the testing grounds. Today we're going to discuss a few things that might have been unclear in the previous build. I posted it to Reddit and got some people who commented that they thought that I was some sort of witch or wizard, that this build shouldn't work, that I was hiding something. And I think a lot of the concern came down to sort of the abstraction away of the heat source and the cold source. People said there must be something happening here that makes this build more or less impossible. It seems too good to be true. I think a lot of people kind of concluded that the heat source was fine, that it made sense, because this is something you could get just from a volcano. So they were kind of willing to say, well, if you have a volcano, you can do this. You don't necessarily need a volcano, and I can, if people are interested, I can show ways that you can get this sort of heat source pretty easily. One of the most straightforward ones is you just dig down to the magma, you create some sort of loop that brings, let's say, diamond on a conveyor rail up through some sort of vacuumed area, and then exchanges it with some sort of fluid or anything in here. That would work. There's other tricks with glass forges, metal refineries, whatever. But I think most people are willing to accept that the heat source was legit. And so the concern was, well, surely this cold source couldn't be legit, right? You say you don't need supercoolant, but here you have a bunch of supercoolant as you're cooling. And there was a sort of accusatory tone, like, well, if the build could work, then why didn't you just make it work? I don't know. But I have 4 degrees from MIT, and I spent a year and a half getting my ass whooped by thermal fluids engineering. So we're not going to be taking guff from any randos on the internet here. Let's show you an actual build that maybe is more convincing than if these abstractions got a little bit confusing. So this build, and I'm going to show you 3 of them, this build is designed to achieve more or less the theoretical maximum that you can get. I could have extended this out even further, but the basic gist is that this system, in theory, if built perfectly, actually doesn't require really any energy at all to run. That the efficiency losses are actually rather small. We basically have 2 sources of efficiency losses in the system. One is conduction through sour gas across this length, which is going to be determined by the thermal gradient across this length. So the difference in temperature between one tile and another is going to determine the efficiency loss due to that. But this efficiency loss is fairly small because sour gas just has a very, very low thermal conductivity. The other sort of efficiency loss is the pump. This pump generates heat. This is supposed to be a cold area. Bit of a disadvantage of that. We could reduce this efficiency loss by using a larger pump. It's kind of weird, but the small pump actually generates more heat per unit pumped. So we could change that around. But I just wanted to create sort of a large build to show what the sort of theoretical efficiency is. And unfortunately, I have not been able to get one aspect of it to work, which is a sulfur recovery system, which I'll get to in a bit. But the gist is this build, and I'm just going to go ahead and let it run because there's no reason not to. So here's these window tiles, 171, 171.3, something like that, right? This build can run basically off of 3 to 4 aqua tuners. Right now we only have 2 on, but eventually we'll have all 4 kick on. See, like this, it cycles a little bit, right? It goes through a little bit of kind of, cycles, but it's a pretty small cycle. It doesn't really matter. But 3 to 4 aqua tuners will maintain this build in perpetuity, right? I have the entire system powered by these couple hydrogen generators up here, right? They're manning the liquid shutoff, the pump, this stuff which I use just to pump some hydrogen into the system so I could get it, I could have an actual working fluid in there. But 3 and a little bit more thermoregulators are required. And a lot of people thought, oh, this build is going to take tons of thermoregulators. They thought I was missing the point or something. They said, oh, but the reason you go to space is the efficiency. That's not really why you go to space to try and make one of these systems. It's a lot easier to make one of these systems when you can have the working parts inside the heated area. But this system works just fine as well. So we have 4 thermoregulators. Again, we only really need 3 of them. And in theory, we could get this down to basically no thermoregulators as long as we were able to create a cold source and occasionally top it off with, right? We could have 1 thermoregulator that ran occasionally, and it would be able to provide all the cold for this. And why is that? Well, here's the thing. We are conserving about as much of the cold in this system as we can, right? If we imagine this is a system that generates cold, and I know that's kind of a wrong way to think about a law of thermodynamics, but if we imagine this as a system that's generating cold, all of the cold that is coming through with this methane is being transferred to the sour gas as it comes up, right? So that by the time it exits, let me just go ahead and clear this, just so we can kind of see the exact temperature that's coming out as. No germs, please. I don't know if that makes a difference, right? So this temperature is about 74 degrees. This is the output temperature of, maybe it's a little bit higher, 74-ish, whatever. It's about 74 degrees that's coming out here, and we have 77 degrees right here. And that's roughly consistent with the thermal gradient that we've established here, right? We are taking all of the cold that we created down here, and we are exchanging it with the sour gas as it comes down. And likewise, this crude oil is doing the job on the other half of the tube, right? This crude oil is exchanging sort of its cold with the sour gas as it comes down, so that sour gas, by the time it reaches here, all of its heat has been dumped into the oil that is then going to be boiled into the sour gas, right? And then over here, all of the sour gas is losing temperature because it's exchanging heat with the methane that you're pumping out. So ultimately, you're getting 74 degree methane over here. You have 77 degree oil coming in, right? You just have a nice smooth gradient throughout this thing, right? If we look at the temperature, right, it just slowly goes up and up and up and up, almost linearly because of the way that we have the system designed, right? Like I have the entry point and exit point at, in a sense, they're ideal, but I'll get into that in a little bit. And so we're not really having to use any cold. We might be saying, okay, well, if you're recapturing all of the cold in the system, so to speak, then why do you even need these thermoregulators? Well, the thing is, this sulfur, right? Only 2/3 of the mass, so to speak, is coming back up here. 1/3 of it is staying here as sulfur. And so you have losses in the system that you need to recover. We're continuously adding, right? We can see the sulfur number just ticking up and up and up. We're continuously adding to the amount of sulfur in our system here. And all that sulfur is at a really cold temperature, right? That's kind of what's going on here. We're not getting a full recovery of all the cold because we're slowly accumulating cold in the form of the sulfur. Now, I wanted to make this video after I had played around a little bit more with a sulfur recovery system, right, which basically would try and do the exact same heat transfer process that we have here, but with the sulfur. It's tricky because the sulfur is a solid here, and that's actually the most difficult stage for it because there isn't the equivalent of a radiant pipe for solids. You have conveyor rail, but unless you run that conveyor rail through something like diamond, it's not going to conduct much heat. And there's a big problem, of course, with putting just a big row of diamond in here, because if you do that, you're going to greatly increase the heat transfer from whatever the top of that diamond is to the bottom. And that's going to up your efficiency losses, right? One of the reasons why the system is so efficient is that sour gas is a very low thermal conductivity, right? So there's not much just direct heat transfer going down. Most of the heat transfer is from the sour gas that's situated here to the pipe that's cooling it, right? That's where most of the heat exchange is going on. This pipe has a thermal conductivity of 120. The heat is a lot more likely to go into this pipe than it is the sour gas that's right next to it, which has a thermal conductivity of 0.018, right? So that's very important. If you added that sort of block of diamond in here so that you could radiate the cold, again, this is not really the proper way to think about it in thermodynamics, but whatever. If you added that diamond block, you would greatly increase your efficiency losses over the length of that diamond block. And so it turns out there's some trickiness, and I'll have to really think about this problem more for how you recover the sulfur. But if you do the calculations, right, for how much cold, so to speak, again, that's kind of the wrong way of thinking about it, but it's just, I don't know, I'm going to go with it because it's an easier sort of layman way to explain it. If you calculate sort of how much cold is being absorbed by the sulfur, the answer is that for every kilogram of crude oil that you're putting in, you need to cool down that sulfur with 104 kDTUs, right? What does that mean? Well, DTUs are sort of a made-up unit in the game, but roughly speaking, a thermoregulator will produce 33,600 kDTUs, right? So just 3 and a slight fraction more of a thermoregulator will keep the system going, assuming no efficiency losses. If your only losses are due to the accumulation of sulfur, then you're only going to need 3 and a very small fraction of thermoregulators. Of course, in practice, we do have some efficiency losses. There is a bit of a thermal gradient here. We've smoothed it out and make it, really, really low, but there is a bit of a thermal gradient here. The sour gas is not a perfect insulator. It is transferring between the layers of sour gas. And also, we just have this mini liquid pump, which right now is producing 500 DTUs, right? Which isn't that big in the grand scheme of things. But again, this is just another thing to consider. There are some efficiency losses, but you can see we've been running this system for a while now, basically the entire time that I've been talking. We actually have, at this point, 2 thermoregulators turned off, right? It's oscillating between turning them on, turning them off, right? We have 3 going right now. Eventually we'll have 4 again. There's the 4th. And it's kind of toggling between 2, 3, and 4 because it's a little bit more than 3 that we need to keep the system cool. But we notice it's still in basically thermal equilibrium, right? These window tiles are all still pretty much at the same temperature, right? They haven't gotten hotter. At least I don't remember what temperature we had of it, but they haven't gotten much hotter if they've gotten hotter at all. This is a system in thermal equilibrium, right? It's working just fine. We have a source of heat up here. We have our source of cold. It's only 3 and a little bit more thermoregulators if the system is at sort of this theoretical maximum, right? That's pretty close to what it is. If you go and check out my Reddit post, you can see the math. I'm not going to go through all the math here. It's kind of basic actually. But yeah, here we have, just again to kind of explain the system, we have a diamond block as our heat exchanger, right? We have hydrogen. These are all running in parallel, right? So if I show this system, each one is their own independent system. If you're confused about how this is set up, I guess watch my Let's Play. I make a lot of these systems, but it's a pretty basic thing where we have controls set to where we want the maximum cold to be. We don't want to cool the air down if it's higher than 195. This is a thing you kind of can almost set at random. This is not the ideal number actually, but it doesn't really matter. It's pretty close to the ideal number. And yeah, pretty simple system. Again, the inlet temperature of our crude oil is 79 or 77 degrees, which is roughly what you'd see pumping it just straight up from the oil biome. Plumbing is everything that you'd expect here. It's just a pump. It's heat exchange, goes into here. Again, if you watch the previous video, all this stuff should be pretty clear. So, right, this kind of just shows that the theoretical maximum, the math that I showed in my Reddit post is correct. But you might be saying, well, this build looks really big, right? This is a really big build. It goes all the way up here. Maybe I don't want to build something that big. And so we have a couple more builds to show you. Let's go ahead and load them up. Compact A. Let's do Compact A first. This is a smaller build. And basically what I did was I just kept shaving off a little bit of height until the system seemed to be roughly in thermal equilibrium, right? Where we reached a point where I had all 4 thermoregulators of my cooling block basically going constantly with none of them really having any downtime. And here's our system. And I'll just go ahead and let this run, right? Again, I've adjusted things to be a little bit more closer to the ideal. The condensation point of sulfur is 161.5, so we kind of want this tile to be closer to 161.5. That way we have a little bit less of a gradient, a little bit more efficiency, right? But this system, I think, is actually just slightly too short. It needs to be 1 higher to have these. Basically all 4 of these should be running pretty constantly, right? And I think that if you gave this system enough time, it actually would warm up just enough to prevent it from working, is my theory. I haven't actually ran it long enough to see that happen, but these very rarely get any sort of breaks, so I think that the system is not quite in thermal equilibrium, but it's pretty close. You could run this for a very long time and not really have to worry here. Where we have the room just packed with natural gas at this point. Obviously, the outlet temperature is a little bit hotter because I just kept shaving off height off the top to see how short I could get it. And as a consequence, I don't really have the input and the outputs at sort of their ideal, but we can get to that in a bit. So this is actually a much more reasonable build. It basically fits on my screen, right? I've got my cooling area over here. I've got my heat exchanger to exchange the cold with the sour gas, right? Again, everything's pretty much as you'd expect it. Here's our pump. Inlet temperature is 77 degrees. Outlet temperature is a little bit higher because, again, kind of proportionally, we're exiting the natural gas at a higher point, and so that's influencing things a little bit because I didn't design it first glance. I've been kind of just modifying this top part, moving it down a little bit to see how close I could get it. I think this is about as close as I can get it. From this window tile down to this block right here is 25 tiles. If you go a little bit further, it's like 27, right? Like, just to give you a sense of proportion here. So yeah, this system is about as small as you can get it, I think, and still process 1 kilogram of crude oil off of 4 thermoregulators. Now, of course, if you're willing to put in like a 5th thermoregulator, you can make the system even shorter. And it's sort of a trade-off between how much radiant liquid pipe you want to put down, how compact you want your build to be, right? You could still have them be like this size, just it wouldn't quite be as efficient because you'd have a much more aggressive thermal gradient. And again, the efficiency losses are going to be determined by the delta T between one layer and another, right? The difference in temperature as you go down is going to affect it. And here, like, we're about at the point where it turns into sour gas here, right? This is 534. We go down, it's like 510-ish. Go down, 500, 470, 460. It's a little bit wonky. It's not quite going linearly in the sense because this is an S shape, so it's like it's kind of going more linearly along the pipe's length. But you get what I'm saying, right? Like, that's the main source of the efficiency losses. And here with this length, the efficiency losses are enough that you basically have to run all 4 of these thermoregulators at the same time. I do want to emphasize, though, you're getting 667 kilograms or 667 grams per second of natural gas from this system, right? 667 kilograms is enough for about 6 kilowatts of power. These, all 4 of them in total, run you about 1 kilowatt of power. So you're netting 5 kilowatts of power. You're also getting polluted water and stuff if you're using this natural gas. Again, we're powering the system just with some hydrogen generators right up here. That's what everything is running off of. But you know, if you were running this off of natural gas, you would still have a very large power surplus, right, on the order of about 5 kilowatts. So still a positive system by and large. I want to show you one last build just to kind of give you an idea of how you can tweak the system to achieve various ends. So let's go ahead and load up Compact B. So Compact B is going to make one small change, and this isn't a huge change. It isn't crucial. It's not going to really in a huge way impact the efficiency of your system, but it is going to kind of redistribute where the efficiency losses get suffered. And so what we've changed here is I've basically just moved this this outlet point for the methane higher up, closer to this end. And basically what this is going to do, I'm not sure if we're going to get a good gradient here, but it's going to create a very strong gradient up here, a much more significant gradient up here, and a smaller gradient down here. And sort of as a consequence, what's going to happen is that this heat source is going to drain down faster, but relatively speaking, this cold source is going to preserve itself a little bit longer. So we see in this one, basically the same build, right? Same cooling block, same inlet point for the crude oil, same temperature, inlet temperature for the crude oil, right? Everything's the same, but we're going to see that this one is going to, because the efficiency losses are kind of being shunted over to this end, right? This heat source will run down faster as a result, but we're going to see these toggle off much more often than we would see in the previous build, because those efficiency losses have just been shoved to the other side, right? And because the efficiency losses are more significant in this more compact build than they are in the larger build, we're going to see an actual, impact. If I change the exit point on the larger build, the really kind of the one that was aiming for the theoretical maximum, we wouldn't actually see much of a change down here, right? Because, in fact, what we mainly just see are just losses, right? We'd see more heat being drained out of the system faster, but we wouldn't really see any improvement in anything else, right? That's how you would get this natural gas hotter. You just drain heat out of this thing faster, right? Plain and simple. That's where you'd get that delta T. But a system like this could work for you if this natural gas is just going straight to a generator and the heat is just getting deleted. In that case, maybe you're fine having your natural gas be really hot, right? That works. I usually have it down here, and I kind of want to make that point. I have it down here, like right underneath where I have my my crude oil, because that's going to be the point that kind of distributes the efficiency losses between the heat source and the cold source evenly, right? And that's going to be overall the most efficient thing that you can do. So if you were designing your system and these two systems were linked, if you cared about both the efficiency of the heat and the efficiency of the cold, like imagine you had space materials and you just had a thermal aquatuner up here that was supplying the cold to down here, you'd probably want to have your exit point be, you know, around here. That way you had a nice smooth thermal gradient throughout the entire thing, and you weren't excessively draining heat from one area or excessively draining cold from the other. Again, I mean, it depends. Some things are harder to do. Like if your source of heat is just magma, you don't really care if you're cooling down this magma. In fact, maybe it's a good thing if you cool down the magma faster than you normally would, right? Because then you can mine it as igneous rock, something like that. It's more resources for your base. I don't know. But notice there just is a little bit of a change here. Before, the exact same setup, we were running 4 of these pretty much all the time. Now we're running pretty close to 3, right? We've gotten a lot closer, in fact, to that theoretical maximum that we talked about earlier, because we've taken all the efficiency losses that were gained by moving to the shorter system and kind of just shoved them into the hot end of the system, right? And so this one is going to be a lot more closer to just having 3 and a fraction run than the last one, which was pretty much 4 running all the time. So hopefully this makes things a little bit clearer. There isn't any black magic. There isn't any witchcraft going on here. You don't have to throw me in a pond and see if I float. It's just simple thermodynamics, right? We're recapturing a lot of the cold, and hopefully I'll be able to come back with a build that does sulfur recovery. And then we might actually be able to see this entire thing run off of just one thermoregulator, right? Or better yet, just have a system that has even more flow, but run off of something like an anti-entropy thermal nullifier, right? Because in total, remember, for 1 kilogram per second here, that's what we have right here, for 1 kilogram per second, we need, with no sulfur recovery, we need 104 kDTUs. An anti-entropy thermal nullifier will provide, I think, 80,000 kDTUs. So in theory, you could still have the system run off of an anti-entropy thermal nullifier. You would just need to throttle this flow a little bit more, right? And of course, the system is scalable the same way. If you want more flow in here, you're just going to need more pipes and more cooling. With a sulfur recovery method, and I have to think about how I want to do that because it is kind of a challenging problem in this game to transfer the heat from the sulfur to the sour gas. It's actually a really difficult problem. If I figure out how to do that, you could run this entire, you could run, 10 kilograms per second, probably off of one thermoregulator. I think the system is that efficient. There's really not much in the way of efficiency losses just because the thermal conductivity of the sour gas is so poor. And yeah, again, hopefully this clears things up. Hopefully this, makes it so this doesn't look just like a lot of black magic. The only reason I abstracted away this over here is because you have a lot of different options for cooling, and I kind of didn't want to dictate which one you use. I thought it was sort of an unnecessary part of the build, but it kind of made people suspicious. They thought, oh, he must be hiding something. This build is too good to be true. It's not too good to be true. You don't really need a lot of net energy put into the system to make it work, right? Like, really the only reason we even need that much net energy in the system that we have right now is just because of the sulfur. And hopefully in the future I'll show you a build that fixes that. Again, I don't know. I've tried for a few hours now, and that's kind of delayed me just putting out this video. So I'll see if I can get it to work. It's a more challenging problem, but it does have rewards, right? Like I don't know. It greatly reduces your power use, but even so, again, I think that just having 4 thermoregulators set up is a pretty cheap price, right? Obviously, you do need to dump this heat somewhere. Right now, I just have a bunch of hydrogen in the room that's soaking up the heat, right? That isn't something you don't want to use this heat somewhere, right? You could use it to generate steam and run that through a steam turbine, or you do whatever, right? You dump it into polluted water and then you water sieve the polluted water. You need some solution for this, but this is a pretty easy thing to do, I think, in the mid game. Again, you don't need any space materials. You don't even really need any steel, right? I've changed this door to an iron door. I kind of mentioned in the previous video that you could do this, right? It works perfectly fine with an iron door. None of these parts really that matter that much. I made these out of steel just because I didn't want them like overheating in the middle of things, right? We see this hydrogen temperature kind of ticking up over time. But you don't as long as you're taking the heat away from the system, this doesn't even need to be steel, right? This doesn't technically need to be insulation. It could be ceramic. I think this is a really cheap build. I think some people kind of got confused as to the thermodynamics of it. They thought that you'd have to be doing a lot more cooling than this. Really, this is all it is. The only cooling you have to do is because of the sulfur and the small efficiency losses. Get rid of the sulfur, and seriously, you could run this thing off of one thermoregulator. All right, I've rambled enough. That's it for this video, and hope this clears things up, and I'll catch you guys next time.